Hey everyone, welcome back to Gemba Lead. Today we're going where the real work happens in semiconductor engineering. Have you ever had a product that passed every single test on the production line, only to have it fail in the customer's hands 3 months later? It's a nightmare for any product engineering manager. The reason is usually a misunderstanding of two fundamental concepts: quality and reliability. Defining quality versus reliability. Let's clear up the definitions. In our world, quality is 100% performance at time zero. It means the part meets the datasheet specs right now as it leaves the factory. Reliability, however, is 100% performance after time zero per the datasheet. It's about longevity. Think of it like a marathon. Quality is the runner showing up healthy at the starting line. Reliability is their ability to actually finish the 26.2 miles without collapsing. Qualification is the thorough process that ensures the design meets standards and verifies compliance before we ever hit mass production. It confirms the device's longevity throughout its entire life cycle. The datasheet, your strategic blueprint. Every good strategy starts with a map. In IC land, that map is the datasheet. We cannot test what we haven't defined. 3 key sections act as direct inputs for our stress plan. 1. Absolute maximum ratings defines the voltage and current limits for destructive testing margins. 2. Recommended operating conditions sets the baseline for voltage bias and temperature during live tests. 3. Package information dictates mechanical and moisture sensitivity tests. Translation, logic, and the physics of failure. How do we turn these specs into a strategy? We use translation logic to map mission profile requirements to accelerated test conditions. We don't just heat chips up for fun, we do it to trigger specific wear-out mechanisms. Examples of stresses: ersten silicon level die wear out. When we take the max VDD rating and add a 10% stress margin for HTOL, high temp operating life, we are targeting silicon failures like TDDB, time-dependent dielectric breakdown. By overstressing the gate oxide with higher voltage, we accelerate the formation of conducting paths that eventually short the transistor. We also activate electromigration, where high current and heat cause metal atoms in the traces to physically move, leading to open circuits. 2. Package level thermal fatigue. When we translate the operating temp into temp cycling, we are looking for CTE, coefficient of thermal expansion, mismatch. The silicon die, the plastic mold compound, and the lead frame all expand and contract at different rates. This tug of war creates mechanical fatigue that eventually snaps wire bonds or cracks soldered joints. 3. Material level HAST and corrosion. For plastic packages, we use HAST, highly accelerated stress test. Because plastic is non-hermetic, it absorbs moisture. By combining high pressure, humidity, and voltage bias, we check for ion-driven corrosion. If the passivation isn't perfect, moisture reacts with the aluminum traces and eats them away. The Rulebook Global Standards. In the Gemba, we don't invent tests. We follow globally harmonized standards to ensure consistency and customer acceptance. JEDEC JESD47. The global baseline for IC stress test-driven qualification. AEC Q100, the automotive derivative with stricter grade requirements. ANSI ESDA specifies standards for electrostatic discharge ESD like HBM and CDM. Execution, sample sizes, and confidence. For tests like HTOL, the standard sample size is 77 units per lot across 3 non-consecutive manufacturing lots. This captures process variation over time. Statistically, 77 units times 3 lots with 0 fails provides approximately 90% confidence that the lot defect rate is less than 1%. If even a single failure occurs, it typically requires a full root cause analysis, RCA. Conclusion: closing the loop. The final step is to verify that the device still meets the datasheet requirements after stress testing. We perform drift analysis, measuring parameters like reference voltage or current consumption at 0 hours and comparing them to post-stress results against drift limits. Only with a signed qualification report citing all JEDEC ANSI standards can the datasheet be marked active and the product released to market. That is the IC qualification strategy. It's about moving from I hope it works to I know it lasts. If you found this technical deep dive helpful, hit that like button and subscribe to Gemba Lead. I'll see you at the Gemba.